So, welcome to another lecture of probability and statistics. The usual drop-in of people coming to class is happening again. So we started with, I guess, 70, then we're 40, now we are 15 or so. So thank you for being here. It's usually very nice to have people coming to actual class. So today we're gonna cover a lot of topics. So we're gonna go through more definitions and rules of probability that are gonna be very useful for later. And then we're gonna touch about on random numbers. So what a random number is and what this has to do with probability and statistics at the end. So let's start because we have a lot of things to cover. So I think last week we were already talking about some of these concepts, so marginal probability and joint probability. When we were, remember, talking about probability of A given B, or when we were just saying probability of A, right? We just didn't put the name on top, but I think the first two we have already seen it. And today the new thing is the conditional probability, but let's just go over this definition. So we say that there's a marginal probability of a subset A when we say what is the probability A over omega without counting for the other subset that might have omega. Okay? So we just do A over omega. This will be the marginal probability of A. That's what we have been doing in the last week, right? Then something that we have also explored is the probability, the joint probability of two subsets, so let's say A and B. So, and that was when they overlap, right? So the events that overlap these two subsets A and B will give you the set of elements that you have to go over the whole omega. So in both cases, the marginal probability of A, it was something like the elements of A over the elements of omega, right? And then for the joint probability of A was the union of A and B, right? So something like that, right? So we counted over the whole omega. That was the key thing. Now it comes a new concept of, the new concept, you probably already know it, that is the conditional probability of A given B. So now we reduce our omega to B, right, in this case, and then it's going to be, what is the probability of A to happen given that B happened, okay? So now it's going to be not over the whole omega, but over B. So this is a very important concept or very important definition that we're going to use later, right? And you will see that we can already use it if you want. So, and it's denoted as PA part B. Okay, don't confuse with PA not B, which was that the other definition that it was A without B, right? That is different topic. Okay, so as always, an example. Let's say that we have a city, right? And you are here trying to cross the street. Maybe you're with your bike. I was doing that today. And you want to go in that direction, and there is traffic incoming in this direction, right? So you usually wait for the traffic light there to get red. The car will stop, and then you're gonna go, right? And when it's green, you usually stay there because if not, you're gonna be hit. So let's say that we want you to see what is the probability of being hit by a car, given that the traffic light is yellow, green, yellow, or red, right? So we can define then two subsets, A and B. A could be the probability of being hit or not. And B could be the probability of the traffic light to be green, yellow, or red, right? And then we can actually, let's say that you have statistically or demographically collected data of how many people have been hit in the streets in one population of one city. And now with the upcoming of the smart cities, now you know the probability of the traffic light in that specific corner to be red, yellow, and green, right? Then you could get all this number together, and you could make what's called the joint distribution, or the conditional probability here, of B and A, or A and B. And here B is in the columns, and A is in the row. So B, the probability of B to be red is the first column, the probability of B to be yellow is the second, and the third is the probability of being green. And then the row of A, the first row would be that probability of A, so to be not hit by the car, and the second row would be to be hit by the car. Then you can see, well, if it's red, there is a fairly amount of chances that you're not hit, which is not 90 or 100%, it's almost 70%. That could happen because some people will not see the lights and they don't care, and then they don't see that the car is coming, or the car is actually crossing red. And then you can see that it's a small chance to not be hit if you're green, and that could be because the person is actually paying attention to the traffic light and then it's not crossing, and so on and so forth. And then you can see the marginal probability would be only caring about A to be not hit and A to be hit, right? And of course, everything has to sum up to 1. So that's good enough. So now, this would be the joint distribution between them, right? Where all they overlap. So what about if we calculate actually, and I will move this guy here, so it's to whatever, here. If we calculate the conditional distribution, say, so now it would be, where is the probability of not be hit, given that B is red? So we reduce omega. Before omega was the whole numbers, right? The whole table. Now omega is V equal to red, right? So the probability of A to not be hit, given that B is red, now it's much bigger because the omega has been reduced to B equal to red, okay? And the same to B equal to yellow, or the to B equal to green. And now you can actually see it much clearer that actually if it's red, you have a higher chances of not be hit, and you have a very low chances to not be hit if it's green, right? And the other way around. And now you can see that the sum of the columns actually sum up to 1 because the whole B equal to red is your omega. Okay? Alright. Hope this is clear, and I hope you have a sense of what you have to do in the traffic if you have a traffic light in front of you. So then let's do some definitions. So let A and B be a length of a finite series. Then you can define, basically, that's what I was saying before. So remember, I was saying just at the beginning that for the marginal probability and the joint probability, it was always over omega, right? Now we define the conditional probability as the intersection. It was intersection, not the union, and the rest. The intersection over P of B. So B becomes over omega. That's the key thing in the conditional probability. Okay? And this was defined by, again, Kolmogorov. So you can see that he has contributed quite substantially to probability, and especially probability. And there was a controversy that I'm not going to go through this. I leave this for you guys. Took this slide from Dennis, who was the previous teacher, and they say that this is not totally correct, but I still agree with Kolmogorov. So, what happens when you have a complement of A? Okay, so let's see how it works, the conditional probability for that. So if you have the complement if you want to know the conditional probability of A complement with B, then you have to calculate the first intersection, right? And if you have omega, and you have A and B, and they intersect in something like that, right? Intersection of the A complement with B would be everything that is not B, everything that is not A, sorry, intersected with B, right? And that's pretty much B minus the intersection between them. Okay? Hope that's clear. So then let's calculate the conditional probability of A given A complement given B, and then we have to do our formula here of, right? The conditional probability will be the intersection of A complement with B divided by probability of B. And then we have already calculated the intersection, so we can actually replace this guy here. And then if you just distribute PB, you get 1 minus the probability of intersection A and B over PB, and that's nothing but the conditional probability of A given B. So the conditional probability of A complement given B is 1 minus the conditional probability of A given B. Period. That's it. Give it to you so you can use it in real life or the exercise or the exam. Okay, it's a helpful definition. Yeah, and then you also can demonstrate it with the set too. So now that was two subset A and B. We can also use this conditional probability with a partition of A. Remember, partition of A was something like we have A and we divide it in different A sub I, right? So what will be, again, the conditional probability of the union of many partitions of A given B? Well, we can distribute our intersection now with B, right? And we get the probability of the intersection of A1 plus the probability of the intersection A2 with B, right? And then basically, if we have defined this guy here, we only have to divide by probability of B, and then we get the conditional probability. And again, if you do the distribution, the conditional probability of the union of two partition given B is the sum of the conditional probability of each partition given B. Okay? Again, nothing crazy here, but just useful for later on. What is good about this? When we define this, that we can actually have the union of different partitions given B, we can make it for many partitions, and you could have infinite number of partitions, or you could have a finite number. And the idea is that you can, if you have a subset of B included in A, and you can partition in A, you can find out B without knowing anything about B. Okay? And this is a cool thing, and it's called the law of total probability, and it's defined that the summation of the probability of B given each of the partition times the probability of that partition, if you sum it together, it gives you A. And to give a sense of how this works is, let's say that this is A1, this is A2, this is A3, 4, A5, and A6, and A7. So n is equal to 7, right? So the first thing will be the probability of B given A1 times probability of A1. This is 0, right? There is no intersection between them. Then it's 0, then it's 0, then it's something here. Could be, I don't know, 20%. Here you have another 30%. Here you have, I don't know, another 30%. 2%, 20%. And then if you sum it together, you reconstruct B by just doing the conditional probability. Okay? So this is useful for many cases, and it's called the law of total probability. And we're going to use it in an example to see how we can actually use this to infer things that we don't know, like B in this case. So there's a proof here that you can actually look at yourself if you want, but it will come to the definition of the law of total probability. So how we can actually use this? Let's do an example. So let's say that we have a deck of cards, and it's a French, in this case, deck of cards has 32 pieces, right? And 2 cards will be drawn, one first and then second, right? So if you know the deck of cards of France, they are black and red, and it can be a club, a spade, and the red are hearts and diamonds, I think, something like that. So let's say, what is the probability that the second card that you draw, that you take, is a black? So you want to just calculate that, okay? So what you have to do is, now you have to take the conditional probability. You have to actually use the law of total probability to infer B from A. So first you have to calculate the condition probability that the second card is black, given that the first one was black, times the probability to be black, that the first card was black. And then you have to sum also the other possibility that the second card is black, given that the first was a red, times the probability of being red. So we are doing this here, right? Black, given that it's red, times the probability of red. Black, given that the first was black, times the probability of being black. Okay? And then we try to reconstruct that what is the probability that the second is black would be our B in this case that we want to create. So how we do this? So we have 2 parts, right? This would be 1 and 1, and this is part 2. So the first part is, what is the probability? So the probability of the second card to be the probability of the second card to be black, given that the first was black. So we have 32 cards, 16 black, 16 red, right? But we already have took 1 black in the first drawing, so we have 15 only in hand. Over 31, because we also have taken 1 already, right? So that's the probability of that the second was a black, given that the first one was a black, times the probability of having a black. Well, that's half and half, 50 and 50, so 1.5, right? Then the second is what is the condition probability that the second card is a black, given that the first one was a red. Then you have now 16, because you have not taken any black from you, so you have 16 over, again, 31, because you already took 1 card, times the probability to be red also is the same as the probability to be black, is 50%, so half. So if you multiply and sum up, you end up with 1.5. So there is 1.5 chances of getting a black as a second card, given in general. No matter if the first one was a red or it was a black. So we have reconstructed B from A. Okay? Second definition of today, that was the first one was the law of total probability. The second is a very, 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 very important rule, which is the Bayes rule. I say very important because it's very important for statistics and for probability, sorry. But it has been applied to many fields, like if you are into machine learning or you are into statistical machine learning, especially, or even some biological concepts can be explained by this rule. And the idea is, the rule is as simple as this. So it says that the probability of A given B is equal to the multiplication of the probability of B given A, so the inverse, times the probability of A divided by the probability of B. That's it. And we show a proof of how this works. Very simple, very, very simple. So Bayes was, not to say a genius, but even more I would say, because with this simple rule, he defined what is called the posterior probability. Okay? So what is here, we call it the posterior probability. What is here is the prior probability, and I'm explaining why we call it like this. And this is what is called the likelihood. And everything is divided by p because it's first because it's a conditional probability, and second because you have to normalize in some way that this actually gets between 0 and 1. But the idea is that if you multiply prior probability times the likelihood of the event to happen, you get the posterior probability, so what is predicted to happen. And you can see that already you can use this if you are classifying or predicting an outcome. You could use previous information multiplied by the likelihood of this information to happen to predict what will happen in the future. Okay? That is the beauty of this. And it's very useful for example, like I said, machine learning, but I have been shown that actually, and I will go back to this when we talk about normal distribution, that our brain has what is called a Bayesian brain, that we use previous information accumulated in the memory, and we actually integrate it with the current information that you're sensing, that will be the likelihood for something to happen, to estimate something that will happen in the future, in the near future. Like, for example, a ball is coming to your face, and you have been hit by this ball before, and you see the velocity and the approximation of the ball, you can actually estimate when the ball will hit you, and then you can actually try to, if it's not so fast, you can try to avoid it. Okay? So the brain actually integrates sensory information and information from the past in the Bayesian fashion. I will try to do some example when we go later to the normal distribution because it's much interesting that just saying. But just for you to get really excited about the Bayesian rule, I just give you some examples. So, why is this true? Well, we have to calculate the probability of A given B, and we know that it has to be the intersection of A and B divided by P of B, right? That's the definition of conditional probability. And then if you multiply and divide by PA in the numerator, you are just not modifying the equation, right? You just multiply by 1. But you basically, now you can actually, this guy here becomes the probability of B given A, right? And then that's it. That's the proof of the Bayes rule. So important concepts usually are not so complicated. What else? You can also, and this is also very important, you can not only do for one specific set, but for partitioning of this set A, right? For A to I as we did it before. The only difference is that's going to be the probability of each subset given B. It's going to be the prior of that, but now you have to sum up all the partitional probability to get B. Basically, we are getting this guy here by summing up all the condition probabilities that we did before, like we did before. And this is also very interesting because if you go to the biological world, let's say, I say that the brain can also integrate information from the past to predict the future. You actually can integrate different sensory modalities like vision, sound, hearing, and touch, smell, to sum it up together. That will be different partition of A, if you want to call it like that, and then to predict what would be for a particular sensory information, what is the probability to happen. But let's put it in a very simple example. Here, how we can use Bayes rule and how we can compare this with the law of total probability. Okay? So let's say that we have 3 boxes. A1, A2, and A3. And let's say that we pick up we can pick up one ball, and then we have three hypotheses that we want to test, right? So A1 was that one ball is red, and the remaining three are black inside the box. Two balls are red, and the remainder are black, so A2. And A3, three balls are red, and the remainder is black, so one black. So we want to see. We don't know how many black and red balls are in the box, but we want to estimate that. Okay? So first we can define our a priori or a prior probability. So each of the probability of the hypothesis to be true has to be larger than 0. And the summation of them, they have to be equal to 1. Okay, so if there is 50% of A1 to happen, the rest has to be 50 in some way, 25 to 25 or whatever. Okay, so this is the probability to one of these hypotheses to be true alone. P of A to J in this case. Then, let's say that we got a red ball from the box, and we're going to use that information to estimate the box. And we don't do it one time, but we do it n times, so many times. Okay? So now, if we assume that the first hypothesis, and we test that there's one red and three black, then the conditional probability of B in our case to be red, given that the hypothesis A1 is true, is 1 over 4, because we have 1 red over 4 in total in A1, okay? And that you have to multiply it any times, so it's to the power of n, okay? If A2 will be true, then the probability of B given A2 should be 2 over 4, because we have 2 red and 4 in total, and you have to do it n times, right? And then if the hypothesis 3 is true, then the probability of B given A3 is 3 over 4, 3 are red, 4 are black, and you have to multiply it n times. So let's do a small plot here. And let's put trials, so it's the n, the number n, so how many repeated times you took one ball and it was red. And then the probability of the three hypotheses we have. At the beginning, if you draw 2, you would say that number 3 is true, right? Because it has a higher probability to happen. You can imagine that as n becomes larger, then since always the denominator is bigger than the numerator, this probability starts to decay, right? And at some point, if you are around 18 times that you have drawn it, every hypothesis has 0% chances to happen, which is not true. One of them has to be true, right? So the law of total probability here doesn't help us to actually infer which hypothesis, which box we have actually. But if we use the Bayes rule, then it becomes better, because you can calculate the probability of A to I, so 1, 2, 3, given B, with the Bayes rule, right? And that will be, first you have to calculate the probability of B given A, 1, times probability of A given, divided by P of B. And then, here is what we can use the summation, then the probability of B given A1, we know it from before, right? It's 1 over 4 to the n. And then P1 will be the probability of A. We don't know. Probability of A is something that we don't know, right? So we can call it P1. And then we do the same in the numerator. We do all the hypotheses, the probability of all hypotheses to be true times the probability of the hypothesis, right? Given B given A. And we sum it together, and we get some number there. That is, in some way, a function of P1, P2, P3, and that's it. Okay? Then we can repeat for A2, and we get another function here, and P3 will be the same. So we have everything now. The probability of A1 to given B, A2 given B, and A3 given B as a function of the probabilities P1, P2, P3. Let's now take a look about this. So let's say we actually try this many times, so that we go to the infinite. If we go to the infinite, the first probability, the probability A1 to be given B, so our first hypothesis, you will see that we have P1, P2, P3, and we have 3 to the n here, which at the infinite will become a very large number, larger than 2 and larger than P1 for sure, and then this probability goes to 0, right? So we can say that actually there is a 0 chance in the infinite, or with a very large number of trials, that A1 is true actually. Let's see A2. A2, again, we have our 3 here bigger number, but the numerator also have here a quite big number, but it's slightly lower than the denominator. So it will gain the denominator in the infinite. And again, the chances of A2 to be true become 0 in the infinite, or in a very large number. Now, if you go to A3, then A3 is multiplied by 3 to the n in the numerator and denominator, and then they will cancel each other, and it will be 1, the probability in the infinite. So actually, A3 is the one that is true in a very large number. And you can see how the base rule was very useful here. It was actually better than the law of total probability. And actually, if you plot this now with the base rule, you get a really nice difference when you go more than 10 trials. Okay? And of course, P1 plus P2 plus P3 sum up to 1 always. In the infinite, and the other 2 are 0, and the first one is 1. Alright? Good. Alright, so today is a potpourri, I call it, of different topics, but are important for, as always, for the future. So we go to a second concept today, sensitivity and specificity. And I think you have heard this many times, but it's actually using the conditional probability, this concept. So when I talk about sensitivity and specificity, and you have to define the true positive, true negative, false positive, false negative, and the best way to see this is when you have a test, right? A medical test, not a test, an exam, but a test. You go and you want to see if you have HIV, for example. You take a blood drop, no, not drop, they actually take some milliliters of your blood, and then they analyze it, and they say you have HIV or you don't have HIV. And then you usually create this, what is called the confusion matrix, right? And then where you have, if it's a binary outcome, 0 or 1, so true or false, positive or negative, you will have what is predicted by your test and what is actually real, right? And when the test say true and it was actually true, so it was, you have HIV, you have what is called the true positive. When the test say you don't have the disease and actually you don't have the disease, it's what is called true negative, right? And then when the test say that if you have actually HIV and you didn't have it, you have the false positive, and the other way around would be the false negative. Okay? And then you can use this false positive, false negative to calculate the sensitivity of your test and the specificity of your test. And the sensitivity will be the probability of the person to be sick, given that actually was diagnosed as sick. And the specificity would be what is the probability of the person to be healthy, so that the test is negative, given that the person is negative. Okay? So with these concepts, You could use, yeah, have HIV here actually, have it in my mind, I was there. So let's say that you use an ELISA test, which actually is blood, and these tests are usually very good. So you have a 99% of specificity and sensitivity. So really quite good test. Let's say that you, for some reason, think you have the disease and you go and you make the test, and it's actually bad news, you have HIV, and so what is the probability that you actually have it, given that the test can say you have the disease? Let's calculate that. So if you want to calculate that, so you start with the priori probability, so we're gonna use Bayes' rule, okay, to do that. And so Q is the probability of yourself having HIV. You can get Q from, I think I have a slide later, of given the risk that you have taken in any situation, and it's but the analysis of big data, people know that if you are actually confronting this risk, you have this probability of having the disease. So that would be Q, okay? So then the ELISA test can have two outcomes. It can say that it's negative or positive, and then you could have the disease or not. So this is what we are representing here. Our omega is that the test say that you are negative and you are actually negative, that the test is negative and you are positive, and that was the confusion matrix that I did before, right? That the test that is positive and you are actually negative, and the test is positive and you are positive. So those are your complete omega that you will have, right? So exactly. So the first one is actually that you have the disease, and the second one is the outcome of the test. Okay. So now let's create the subset that you need to create. So let's subset a subset K coming from Kranken in German. So you're sick, and you can be then sick, and the person, the test say no, you're not sick, or you can be sick and the test give you sick. So these are the possibilities for K, right? And the probability of K, we call it Q, right? So it will be actually so then the subset of negative results from the test will be that you are sick and the test gives you negative, you are not sick and the test gives you negative. So K and N are basically complement, right? Well, complement in the last one. So we have defined the probability of K. We know Q. We know the sensitivity in values, and we have to calculate, to create the Bayesian rule, we need to know what is the probability of not be sick given that you are sick. So what is the probability that the test say that you are not sick given that you are sick? And what is the probability of not being sick given that the test say that you are not sick? That is the specificity, right? The sensitivity will be when both test and the test and the actual outcome is true, so that you are sick and the test say that is sick. And the specificity will be the other way around. Remember, I don't want to confuse yourself. I think I'm saying, but it's always coming to here, right? So the probability of being sick, given that the text say that you are sick, is basically the true positive, right? It's always there. The probability of the true positive. So with those things together, you can use the Bayesian rule. And now we plug in all what we have already derived, and then you can get what is the probability of being actually sick, given that the test say that you are positive. And then you put it together here, and then yeah, you can get the complement of P, you're not sick, is 1 minus Q, and the probability that that the test says that you're positive and you are not, and you're actually sick, is 1 minus the specificity. Then if you put it together here, all the P and Q's, and replaced by these two guys, you end up with everything with respect to P and Q. P of the sensitivity and P of the specificity we know because it's 0.998. We just have to find out Q, and that's what I was saying. There is epidemiological data, that's what I wanted to say. So people that study big amount of data, nothing collected. And then you could have some graph like this that is say, given your own situation, wherever you live, who is your surrounding, and what you have been doing in the last month, you have some risk of getting infected by HIV, and then you can plot this, and then you can find, let's say that you are, and I think this is this is the probability, and these are the amount of people per mile, whatever. And then you can actually find yourself, let's say, around here, because you end up there. So your P is 1/3. And then you actually can plug that in number, and then there is a 33% chances that you actually are sick, given that the tests say that you are sick. So it's pretty low. Okay? So just to give an example how you can use the Bayesian rule to prove how a test is good or is bad. All right, another example. Let's say that we have 3 boxes, and these boxes have an amount of black and white ball inside the boxes. Basically, what you see there, and then you pick randomly. You choose randomly one ball, okay? And you want to know that ball from what box comes. So imagine that you have 3 boxes in a spinning wheel, and you spin the wheel, and then you randomly choose one ball. You don't know from which box is what ball thrown, right? And then you want to find it out, just because of what you have chosen here. It's a black or a ball. And let's say that you actually have thrown a white, right? So now we want to find out what is the probability of this, the box that you choose it, given that the ball was white. So if you already see that for the box 1 you have only 1 white, from the box 2 you have 2, from the box 3 you have 3. So chances are that you probably pick it from box 3, but you don't know because it's happening randomly done, right? So let's see how we do this. So to calculate, always the base rule is you always calculate the intersection over PB, okay? So that's basically what you do. And so you have to first calculate the intersection. So the intersection of the box I with the ball white will be the probability of the box to be, the probability of white to be, given that you choose it from box I, times the probability of box I. And basically, it's easy because these guys have 1 ball that is white, these guys have 2, and this guy have 3 balls that are white. Then the probability of each of these boxes is always 1/3, because you have 3 boxes. So that's it. It's easy. The probability of that the ball is white, given that the box is coming from a particular box, it will be directly I divided by I plus 1, because you always have the number of white plus 1 in total. Okay, so in the first case I is 1, so it's 1 over 2, right? In the second case I is 2, so you have 2 over 3, so 2 white over 3. And the third one is I is 3, so you have 3 white over 4. Okay? So that's, in this case, easy to put it in this way. So let's now calculate the probability of a ball to be white. So if it's coming from box 1, it's going to be 1 over 2. So you have 1 white and 1 black, times the probability of being from that box. Then the second is 2 over 3 times the probability to come into that box. And the third one is 3 over 4 times the probability of this box to happen. And you sum it together, it gives you around 64%, right? So now we can actually calculate the probability that that it comes from some particular one of the 3 boxes, given that you got a white, right? So now you use the Bayes theorem, or the conditional probability. So you are using Bayes theorem here, the conditional probability, basically. So if you choose 1, if you start with box 1, the probability of coming from box 1 intersection with white, we know that it is 1 over half times the probability of that box to come, divided by, we have calculated here the probability of white. And then you have 6 over 23 is your probability that the ball came from box number 1. Then we repeat that for box number 2, and it gives you 2 over 23, so a little bit higher probability. And if you do it for number 3, it's actually the larger probability, so most probably came from box number 3, which is not a surprise, because we know the result, right? But if you don't know what box was, actually, you will say it coming from box 3, because it has the higher probability. Okay? I know it sounds, from some of you might be very simple, for some of you, since it's early in the morning and I just spit everything here, it might be confusing, but I hope you can listen to me and go through it, and I think you will find it out very easy. Okay, so these are the numbers, so it's slightly higher the probability now to be in box 1, given that you got the Y. So, other way to do this, the same, it will be graphically. So basically you have 3 boxes. You start from here, right? And you say, what is the probability? You pick one ball. What is the probability to be one of these boxes? Well, it's always 1/3, right? And if you are in one of these boxes, then you have, for box 1, you have 1.5 chances to be white, or 1.5 chances to be black. If you are here, you have 2/3 to be white and 1/3 to be black. And if you are here, you have 3 over 4 chances to be white and 1/4 to be black. Okay? And then you can start doing. So you choose a case, let's say white ball, and then you calculate the probability again to be white. How you do it? So you come here, you say 1/3 times, you continue here, 1.5, right? Then if you are in this box, you come here, 1/3 times 2/3. And then you have to sum the 1/3 here, and then if you are white, you add this path, so you are 3/4. And then you multiply together, you sum it together, and you get the same result that we did before. And then to calculate the intersection, you have to just pick one box and one ball. So you will go, for example, for box 1, you will go in this direction, 1/3, and then you will go in this direction to white, is 1.5. And then you have your probability of intersection. If you do the same for the others, you can do it for the other box too, but let's just continue with box 1. Then how you calculate box, probability of box being from what box 1, given that it was a white, you just divide this and this guy, and then you get it. Okay, so it's another way. Not good for when you have a large problem. So you have 100 boxes, and more than 2 ball type of ball, probably it's not a good idea, but if you have a simple problem, maybe I make it easy for you too. And actually, this is a simple coding or algorithm to do decision tree, right? Something like that. Okay. Third topic of the day that has to do with what we have seen, but it's actually a new concept, what is the concept of stochastic independence. So remember that when we said something like we have an omega, and we have A and B, and they overlap, they have something that they share. Okay? But if we have another two sets, let's say C and D, and they don't overlap, then there is nothing that they share, right? And this sharing, we can think about independence, okay? Or dependence. One depends on the other, one not. So, stochastic independency of two events will be that concept, that the two events have nothing to do with the other. What could be, for example, when you're flipping a coin, every time you flip a coin, the outcome that you get now has nothing to do with the outcome before, because there is no way, except that they are in some way manipulated the coin, right? If not, other will be tossing the dice, so the outcome that you get in the first throwing of the die has nothing to do with the previous one, right? So that's the idea. So, but let's put it this way, and sorry that I scratched there, but let's say that you have, you actually toss a die 25 times, and you do three things. From the 25 times, you actually read the die and you annotate. Then, for every time that you throw the die, you ask a kid to guess what would be your number that you're going to get. And the third scenario would be that you ask a computer that randomizes a number from 1 to 25 and you put it there as a string. Okay? With replacement, right? You can repeat it, the numbers. And then you will get something like this. And I don't know if you can guess who will be who. Who is the actual outcome from your dice, who will be the computer one here, and who will be the key. There is one that I think you can guess. Who will be the key? The kid, the children. What do you think? The first, the second, or the third? Any guess? You can be wrong. It's totally fine. It's really... The third, the kid. It could be, yeah, but actually it is the first one. And it's the first one because you can see that there is, yeah, you said. Wonderful. That is actually the case. As a human, you would try to not repeat the previous one because you already have a bias that it is random, how it's going to happen that you have two at the same time. And that's what I say a kid, because the children would probably be even more biased than it. And you probably have now the knowledge that should be, actually someone should be repeated, right? So actually that was the kid. Actually, that was the computer generated, and that was the actual outcome. So generated something that is stochastically independent is really hard to do. Even for computer, when you if you use MATLAB or whatever, and you say random number or whatever, it's not true. It's a not true random number. It's always a sequence, and what it does is just choose part of that sequence, the algorithm, because except you are really doing something like quantum computer or something very on the core of the stochastically, it's really hard to generate something random. The other way is, that's what when we do experiment, that when we do research, for example, you have to test in a human different conditions. Let's say how people walk with eyes open and eyes closed. Then you have to randomize the sequence so the person doesn't know which sequence will happen to them. And then the best way to do is actually, if you have 20 conditions, write down the numbers in a paper, put it in the back, and choose from them. That will be the most close to be a random sequence to do it. If you do it by computer, it will be probably biased in some way. And that is what I wanted to actually emphasize here. And this can be defined basically by that. If you have two sets, right? And there is stochastic independence. The interception, the probability of interception of them is the multiplication of the probability independence. That's it. So that's basically it. It's what I was saying. If you have two sets that are not sharing anything together, you can actually multiply the probability of them separately, and you will get the interception of that. They are independent. Sorry. Just saying things that are not really correct. They will have an intersection, but the intersection is independent, okay, of what happened previously. So that will be, for example, you get just throw a dice and you get a 1, then the next one you throw the dice, but you get a 1 also, so you're sharing the 1, but actually the first one of the throwing dice has nothing to do with the second throwing of the dice, okay? And if you happen to have two stochastically independent events, then the Bayes rule becomes very simple because the conditional probability, becomes very simple because now the intersection is just the multiplication between them, and then you can actually cancel out PB, and then the probability of A given B is just the probability of A because there's nothing that A and B share. So it doesn't matter if B was 0, 1, the probability of A is going to be always the probability of A. And the same you can say for probability of B. Okay? So that's also an important concept. So it doesn't matter how it came before, the probability of A is going to be probability of A. So there's no point to do a conditional probability on two events that are stochastically independent. That's another way to put it. The stochastic independency on the complementary. So let's say that you have A and the complement of B. So if the A and B are stochastically independent, then the probability of A and complement of B is also going to be stochastically independent. And I think there is a small proof here, so you have to start. So if they are independent, this should result in the multiplication of B of A times B of complement of B. So we start. So the probability of A intersection with B complement is the probability of A minus the intersection between them, right? So I think we did that. If it's A and B, and this is intersection, B complement will be everything that is not B, right? And if you intersect with A, it's going to be A minus this intersection that you have here. I hope this is clearly seen. So B complement is everything here, right? So we will hold A, and it will, but if you take the intersection, you actually put in some part of B, so it cannot be B complement anymore. So you have to subtract the intersection between them. Okay? So if you do that, and you know that A and B are stochastically independent, then you can replace it by PA times PB, and then you can just take PA as a common factor, and then this is nothing but the probability of B complement, and then you can demonstrate that the probability of A given the probability of A intersection with B complement is the multiplication of probability of A times probability of A B complement. All right. You can also, if you have subset or partition as a subset, and they are stochastically independent, then again, it will be just the intersection between them is going to be just the multiplication of them. So you can actually divide this problem in many independence events. That is something. Okay. So to have a sense of this, let's do again an example. So let's say that we have what we have here. Well, we have more than that, I thought. So we have around 30 people. So what is the probability that you guys will share a birthday? You would say, no, not so much, right? But let's say that you have n people here, and I say j, so n minus j being the people that are already sleeping, but I don't see many people sleeping, which I'm very happy. Let's say that J are the people that are not watching, are just watching this video. And you have this number of people, and you want to know how many share a birthday. And then you can ask yourself, what is your birthday? It's actually a nice social exercise. And let's put some assumption. Let's say that the year has 365 days, so there is no, let's call it year. And let's say that every birthday has the same probability to happen, so there was no war or there was no disease that everybody has died and then they need to get more children. And they say that there is no twins. You didn't come your brother or sister to the class. Okay? So it's just you. If we take this, we can say that you and the next you is independent from you. Right? You have nothing to do. You maybe share some genes from the monkeys. I don't know, but nothing else. Okay? So let's say that now I have to number you from 1 to k, whatever number it is, right? And then we have to find omega. Omega will be all the dates, all the possible days of the year, multiply each other because you are independent, so to elevate it to k. That is our whole omega, okay? So each of you could have a birthday between 1 and 360 days of the year, okay? And yeah, WI will be your birthday for you particularly. Okay, so we say well, omega is 365 to the k, and then it's easier to calculate the opposite. So as always, it's a nice trick to calculate the probability that no two persons share the same birthday. So the opposite, right? They don't share the birthday. So we call it D, that. And that would be, for each year, you have to subtract one person, right? And you have to multiply each other. So basically, that person have a day from the 365 that you are not sharing, so you have to subtract it, and then you multiply k times, right? For all of you. And we calculate D. So the probability of not sharing, that you don't share any day, is basically this multiplication divided by omega, right? We're just doing the marginal of D, right? So the number of D over the number of omega, okay? Then we can calculate now the probability of you actually sharing a day, a birthday, which is 1 minus that, right? It's a complement. And then will be 1 minus that guy. So we have a formula here. So depending on depending on k, is actually the probability that you have. And then you have that. If you are 25, which you are more than that, you have 56 chances of sharing a birthday. Now, if you get to 65 students here in this room, you actually have a 99% chance of sharing a birthday. So in the first day of class, I think some of you were sharing, or I was sharing a birthday with. I am the 27th of November. So if somebody's from the 27th of November, we are already proving that. So it's actually pretty interesting. And I think it's something that we don't really think that could be such a number. So an idea of how conditional, how we can actually use the combinatory on that. All right, so I think this is the last topic of today, and it's an introduction to random numbers, which is the key thing to distributions, right? So what is a random number? Well, how we define a random number? So it's basically a function. You can think a random number as a function that maps an event or a set of values from an omega to a real number. Okay? That's what a random function does. This is what your algorithm will try to mimic. It will get a set of data numbers, and it will do the function that will select one of those numbers randomly. Okay? And put it to you. And then you can think in this way, so you have an omega with a few W or many W that belong to a subset A, and you want to map it to a linear scale A in the real spectrum, a real space. So a discrete will be the function valued by omega, right? By the function valued in discrete set of the set A, and we call it a realization. And you will see quite soon what I'm talking about realization, because you could have a continuous random number, which would be infinite numbers, right, on each other. But this sometimes in reality, or in our reality, doesn't happen. You will see how that. For example, the dice have 6 faces. You cannot have 3.5. You will see that this is actually happening. Okay? So a realization will be when the random number is discrete. So, like I said, let's go for it. So let's say that we have 2 dice, right? And we toss them, and each of them will have a random realization, right? When you throw it, and each of them will go from 1 to 6 discretely. And let's say that you want to know the sum of them, the probability of some of them, right? Or the expected value. We'll go through this now. So one could be 1 and the other 1, 1 and 2, 2 and 3. We already have seen this, right? So let's say that, for example, allow us to have the probability that the sum of them, the throwing the dice 1 and 2, are equal to or less than 11. Okay? And it's that what I define it here. So, again, slowly introducing to what a distribution is, then a discrete random number, again, we can define it as a function from omega to the real, right? And the probability of the random number to happen is basically defining as what is the probability of having an element from that omega such that the random number of that omega, so the function applied to to W, is equal to such a number. Okay? And that is what you call P of the random number to be that particular number. Okay? That is the probability. And that is difficult maybe to graph like this, but you can actually, I think I have a plot here, yes, later, but let's put it that way. Let's say that you have an exam, and you have many students. You have a sample of 100 students. So what is the probability? They say it's a really nasty exam and nobody passed. So what is the probability that you're actually gonna pass the exam? And then, so what is the probability that you're gonna get what would be the minimum? A 5, a 4, right? The probability of X equal to 4 is gonna be something like maybe very low. And then you will have 1, 2, 3, 4, and 5. And then maybe you have a big probability, 90% of getting a 5, and maybe 1% to get a 1, 1%, 10% to get a 1, and they go really bad like this, right? So what is the probability of a particular value to take this value? Okay, what is the probability to get a 5, to X equal to 5? Okay, that's the idea of this. And this can be applied to the union of subset of A, as always, and basically that the random number belong to A is the union of all the probabilities that you have. Don't you worry about this too much. I want you to come to I think this is the example that I want to say. So let's say that we take a coin again and we flip it 3 times. Okay, so we throw it 3 times, and again 1 could be a head and 0 can be a tail. Right? You do that. So our omega is again 2 possibilities, 0 and 1, 3 times, so it's 2 to the 3, so you have 8 possibilities, right? And then, oh, I always do that, sorry. And then you are interested of the sum of them, okay? Of the outcomes of the 3 times put it together, right? And let's say that you get, for example, 0, 1, and then you have 3 times, the summation of 3 would be, it could be 0, 0, 0, right? It could be 0, 0, 1, it could be 0, 1, 0, and so on and so forth, right? I'm not going to write all of them, right? But for example, the summation of the first one would be 0, that's what I'm saying here. The summation of this would be 1. This also will give you 1, but 0, 0, 1 could be your 2, and so on and so forth, right? You are interested in the sum of the 3 outcomes, right? So the probability of x to become 0, that's what I was saying here. The probability of x to randomly become 0 is 1 over 8. X in this case is the sum of them. Okay? I don't know if you're getting the graph on this. So now what is the probability that you sum the 3 times that are randomly toasted 3 times and it gives you a 0? Well, the omega we already know, I put it again, is 8. Right? What are the number of events that the summation will give you a 0? Well, it's actually only 1. When the 3 of them give you a 0. So it's 1 over 8. What is the probability of getting a 1? Well, it could be 0, 0, 1, 0, 1, 0, or it could be 1, 0, 0. This also gives you 1. So the probability of getting the summation to be 1 is 3 over 8. Then what is the probability of getting a summation of 2? Would be this case, and I'm missing 1. So 1, 1, 1, 1, 1, 0, 1. Give you 2. So 3 times, right? 3 over 8. And you can do the same for the 3. The 3 has to be 1. It's only 1 possibility, 1 over 8. Okay? So that's the idea. You can, with random numbers, you can now make summation, for example, multiplication, division, whatever you want to do. So let's say now that we toast a die now instead of doing a coin. So we toasted 2 times the die, and we are interested again on the summation. So now our omega will be 6 either possibilities. 6 are the outcomes, 1, 2, 3, 4, 5, 6, there are 6 outcomes, and you toasted 2 times, so your omega is 36, okay? So what is the probability that the summation will give you a 2? Well, again, the first die has to be 1, and the second has to be 1, right? So you have only 1 over 36. What is the probability of getting a 3? Well, the first has to be 1, the second has to be 2, or the first has to be 1, and the second has to be, the first has to be 2, and the second has to be 1, that gives you 3. So there are only 2 possibilities. And then you can actually do this. And then it comes what I wanted to show you. If you do that, you can actually build what is called a distribution of the random numbers, okay, for the summation. And you can actually build that by just doing this table that we did here, right? And then from there, you can actually calculate what is the probability that the summation will be larger than or equal to 11. Well, you should just come here. 11. And you just sum the probability from there to the right. And this is an important thing because you will see that later for statistics it's very useful to take a portion of the distribution and use that portion to calculate something, for example. Where the probability of making an error, well, you want to be on the size of the tail, right? That's very low the probability, for example. Okay? So if you see it's 1 over 12, exactly. So it will be larger than 11. It's the probability of having 11 or 12, the last two. And it will be the same graphically finding this point here. Okay? Is that more or less yes?
Professor, you are saying that if I throw a dice twice,
yes,
the higher probability that I will get total sum 7 compared to all other numbers given this graph.
The probability of what?
Total sum.
Yes.
If I throw a dice.
Yes.
Total sum becoming 7 is higher probability than all other
Yes.
total sums.
Yes. Because you have many combinations. Exactly. You get to get a 7 between the two, you have so many, there is a higher chance to getting that than to getting the other. Okay? And that is the soul of a distribution, right? How many counts you have on that.
So it means that in Monopoly, if you get 2 chances, the probability that I get 7, then
you see, you already can cheat on
I
that.
can buy some.
Very nice. Very nice. Okay. So, and from that you can actually calculate expected values. The expected value is something that we already have seen before, and I will just put it here as a definition. It was Huygens, I think, whatever it's pronounced, was actually gave it to the and come from gambling again. This is her Huygens, or I don't know who from where he was from. And basically what he defined was that, and he put it in this way. So let's say that we have a wheel of fortune, right? Again, if you have seen this in the TV, you have the wheel, and I think I have a funny thing here. Yeah, exactly. So you have the wheel, and whatever it comes, the wheel stop, you will get a prize. In this case, it's a binary price, but it could be many prizes, right? And let's say that each of these regions of the wheel, right? Let's make it more serious. We have a probability associated with that. Remember that we did that when we did this. I think we did it like this: 3, 1, and 2. So they have more probability to get a 3 than a 1 and a 2. Well, this could be the same. So each of these spaces have a probability. And each of these will give you X amount of euros if you count there. The typical one. Sometimes it's a car, it's a vacation, a house. It's always like that. It's boring. It should be more like they give you, I don't know, bitcoins or whatever. So they give you that. So let's say now, what is the probability? What is the expected value of that? Okay? So for that you have to get always the expected value, you will need to know to repeat the experiment many times. We did that, we remember that we did that with the fair game. We say if you play the game many times, are you earning money or losing money, or is fair is equal to 1. Right? So you have to repeat the experiment anytime, okay? And it will pay you the money in the end times. And this is basically the definition of the expected value. So basically it's X of W for J, where you have your wheel, and each of these are your J of W. Each of them will give you X amount of money. It's a function that maps money, or W, areas of the wheel to money, okay? And then you have a probability to end up in one of these, which is H to J. If you multiply together and you sum for the event to happen, for the many times you did that, then you get what you expect to earn or lose, right? So it's basically how the probability of getting the event times how much money they give you for that event to happen, okay? And that is also when you repeat that, this will be for one event. If you repeat that many times, then you have to divide by n, and that is what's called the law of large numbers. And this will come useful later as we continue with this lecture. So that's basically the expected value of large. I'm just keeping a few here because I don't want to lose you in what is important. So that is what is called expected value of a number. So, and you can think, if you're talking about how a serious event is actually stabilizing over time to give you an expected value, what measure in statistics from high school or from whatever is actually give you the sense that you expect that number to happen? Can you relate to that in some way? Any of them?
Average.
Perfect, wonderful. The average. The average of any set of number is the expected actual value, because it's what you expect, more or less, a little up or a little down, the value that you expect, the average, the mean, arithmetic mean. And you will see later that this is actually a proof that the expected value of a distribution is actually the average or the mean of the distribution. Okay, the only condition is that in this, if you have infinite number of events, that has to be larger than infinite. If not, you cannot actually calculate the expected value. Okay, it has to be a finite number. So let's see what happens with the dice. Let's say that you actually throw a die, and you throw it many times. You throw the die n times. So every time that you throw the die, there is always the probability of 1 over 6, right? To get a 1, there is a probability of 1 over 6 to get a 2, a 3, a 4, a 5, or 6, right? So if you multiply the actual value of the dice that you get, the outcome, times the probability, and you sum it together, you get the expected value. And if you do that, the expected value is 3.5. So that is what I was talking about realization. This is not a realization. You cannot get a 3.5. But in average, you will get something between 3 and 4. Okay? That is what your expected value will be if you throw a die many times. Okay? Yeah. Another example, a very interesting example. What is the expected maximum value that you can get from tossing the dice 2 times? All right. Again, we are tossing the dice 2 times. Every time that you toss it, you can get 1 or from 1 to 6. So you can get in total 6 to the 2, 36 values, right? And we are interested on the maximum value, okay? So again, we have to calculate what is the probability to get 1 and 1, right? To get, so this is the thing. So let's go slower. We are talking about the maximum value, right? If you get a 1 and the second throwing of the dice you get a 1, the maximum value is 1 because that was the maximum that you got. So the probability of the maximum to be 1, right, is 1 over 36. If it happened, what is the probability that the maximum is a 2? Well, it could be when you have a 1 and a 2, when you have a 2 and a 1, or you have a 2 and a 2. Those are the cases where the maximum value was 2. Then it's 3 over 36 because you have 3 possibilities. What is the probability to get that the maximum is a 3? Well, you have 1 and 3, 3 and 1, 3 and 2, thank you, 2 and 3, and 3 and 3, right? 5 times. So 5 times you can get it, all right? And then we continue, blah, 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 7, 9, and then you will start to decrease again, and then decrease. And then the expected value of the maximum to get the highest is now 4.472, because what you do is the maximum of 1, the maximum of 2, the maximum of 3, the 4, 5, 6, and so on, times the probability of this to happen. You sum it together and you get the expected value. That was nice. And we can do another one with flipping a coin. Again, head is 1 and tail is 0. And we're flipping the coin 3 times now, right? So we're going to have 2 to the 3. Sorry, that will be 8, our omega. And then let's say that we are interested in the event that only 2 heads, you get 2 heads, right? What is the probability for that to happen? So it could be that the first is not tail, it's not a head, sorry, and then the next 2 are a head, and so on and so forth. So every time that you have 2 ones and 1 0, okay, that you have at least, sorry, that you have at least 2, so you can have 2 or 3, right? So what is the probability of that to happen? So you have 1, 2, 3, 4 over 8, 1.5. So now, let's say that you actually are cheating and you know that the first one is going to be actually a 1. Then you can reduce the set, right? And because you know that the first is 1, and you are actually interested in, or again on the probability of A, so that at least 2 are heads, right? And then you can reduce our omega. Now it becomes, well, I don't know if I can put it like this. It becomes B omega, because omega total was with all the possibilities. Now we are knowing that the first one is a 1. So our omega is reduced, so to 1, 2, 3, 4 from 8 that was at the beginning. So yeah, example number. And I think this is a very last example before you start hating me, and we can release our attention on the concept. The last one is about for positive and for negative, that combines also condition probability, what we have seen before. So let's say that you are designing a circuit, and the circuit goes into mass production. We are really good, and now they are producing millions of them per year. And you know that you have a failure rate of 0.01%, 0.01. So 1% of them, no, 10% of, no, 1% of them will be actually failing, right? Failure rate. And they will have a probability to broken of 0.01, okay? So you also know that this device is a medical device, actually. And that you have a mechanism to test if the device is broken or not before it's released to the population, okay? And this test it has a probability of 0.1 that is actually the circuit is broken, and the test has said that it's okay, so pretty low. And then there is a probability of 0.05 that is and that is broken, and the test is say that it's okay. Just trying to remember the whole exercise. So we are interested in the probability that a device that was tested okay is actually delivered to the population in an okay status. Okay, so that you are actually delivering things that are really working and not that are broken. Okay, so we have to set up our program here, and A will be the set of circuits that are okay, and B is the subset of circuits that were testing broken. Then, what is the probability of the circuit to be okay? Is 1 minus the failure that we know. Okay? 99%, right? Then what is the probability of the circuit should be okay given that the circuit was testing, what is the probability of the circuit should be tested broken given that the circuit was okay, 0 point from what we had defined before. And what is the probability of the circuit testing broken given that it's not okay? That's what we defined before. So if we use the basic formula again, and you put this number together, the probability of the circuit to be okay delivered to the population, given that the circuit was tested okay, is 99%, which is pretty good. These are the true positives, right? And then the probability that you will send something that is not okay, given that the system was tested broken, is 0.08. So it's not so good. Okay? And I suddenly stopped it here. Sorry, this lecture I know is quite dense and you have a lot of concepts here, but are all important. I hope you have a few key concepts together. Conditional probability, how this conditional probability can use it for the law of total probability, how it can base rule to come to this conditional probability and what is in some cases better than the law of total probability. That then you come to the concept of this sensitivity, specificity, true positive, true false positive. These are concepts that you use later. And a little bit on distribution with random numbers. Okay? So if you are somehow in your head something on that today, you're already very happy. If not, you can always ask me a question. Okay? And I will see you next week. Thank you.